Hello students, very good morning to everybody. Let's continue our quick revision on electrostatics. So we are continuing the revision of electrostatics and this is the lecture 2. In the last lecture, we have discussed up to electric dipole. Now, this is the uniform electric field. Have a look at it, everybody. This is the uniform electric field. So, when there is a uniform electric field is considered, I am just placing a dipole within it. So, this is the dipole where minus q is located here and the plus q is here. So the distance between these two is 2a and this is the direction of the dipole moment p bar. We all know this. And this dipole moment is making an angle theta with electric field. So what you should understand, this p bar and e bar are very important here. Both are vectors. P bar and E bar. So the same thing will also repeat in magnetism chapter also. Now, as this is the electric field lines moving, there is a huge positive charge you have to imagine here and there is a huge negative charge you need to imagine here. So from the negative charge to the positive charge only the field lines will be moving. In this, there is a negative charge here. Due to this huge positive charge, there is an attraction here. So this negative charge will be attracted to positive charge in this direction. And this positive charge will repel this in this direction with some force here, with some force here. I am not going into the derivations of this. So what is the area we are focusing is? So the torque experienced by this electric dipole when it is kept in a uniform electric field. So the torque is equal to, so I am writing here, P bar cross E bar. So what is that? Torque is equal to, if you write the magnitude, so that will be P E sine theta. What is this theta? That is important. What is the theta here? Theta is the angle between P bar and E bar. This torque can be maximum, this torque can be zero, this torque can be minimum. That depends on the theta value. In the same way, so there is a potential energy. So this is what there is a potential energy expression even, that is U is equal to minus P bar, U is equal to minus P bar dot E bar. As potential energy is a scalar quantity, there is a dot product is taken between P bar and E bar. Okay, this if you expand, that will be minus Pe cos theta. See this. So this potential energy also can be minimum, can be maximum, can be zero. And one important thing you should understand. So whenever this potential energy is minimum and that is the position of this dipole is called a stable equilibrium. And whenever this potential energy is maximum, so that position of this dipole is called, it is at unstable equilibrium. At stable equilibrium, there is some angle. At unstable equilibrium, there is at that particular angle. You know, that particular angle will be substituted here. You will get the torque also. At unstable equilibrium, you can find torque. At stable equilibrium also, you can find torque. We are not going into the details of it. We are not going into the thetas of it. For example, so this theta is 0, torque is 0. This theta is 0, the potential energy will not be 0. Right? This theta is 0 because sine 0, 0, torque is 0. This theta is 0, right? Cos 0 is 1. So the potential energy is minus Pe. Minus Pe is the minimum potential energy. So that means the body in the stable equilibrium. When the body is in the stable equilibrium, ಇಲ್ಲಿ body andre the dipole, electric dipole. When the electric dipole is in the stable equilibrium, so the torque is 0, right? So, imagine a situation, initially the electric dipole is here, this is minus q and this is plus q, initially it is here, right? Initially it is like this. From this position, listen, from this position, so what I said, this is 0 is the angle between P bar and E bar, so the torque will be 0, so that means there is a body in rotational equilibrium and it is also in the translational equilibrium, because one force F1 is in this direction and another force F2 is in this direction, both are same. Right? So the body is in translational equilibrium as well as rotational equilibrium, my dear students. Now listen carefully. Carefully you listen. In this case, the body is in at the minimum potential energy it is possessed. So that means it is in the stable equilibrium. So very important point is that from here, if I disturb this dipole like this, if I just disrupt this dipole like this and release, what happens? So it makes, there is a now there is a torque. The body is not in rotational equilibrium, right? And the same way body is not in translational equilibrium also. So definitely, the body is only not in the rotational equilibrium. This will be in the translational equilibrium. Okay. So it will not in the rotational equilibrium. Agagi, it will start oscillating. And that oscillations will have the time period. What is the time period? So the time period of those oscillation is 2 pi square root I by PE. 2 pi square root I by PE. So the same things, for example, there is a uniform magnetic field I have considered here. So uniform magnetic field B bar is considered here. So there is a magnet which is placed here, a bar magnet. There is a south pole here, north pole here. You know, the magnetic moment will be directed from south pole to north pole. Look at this. So the length, the distance between two poles is 2a. Here also, magnetic moment and the magnetic field are at an angle theta. Similarly, you get the torque associated with this, torque experienced by this magnetic dipole, so which is mb sine theta. Potential energy associated with this dipole, so minus mb cos theta. And the time period of oscillation of this bar magnet, 2 pi root I by mb. See here, all the formulas are same. So wherever there is an electric field, we have got magnetic field. Wherever there is an electric dipole, we have got a magnetic moment. That's it. Right? See, PE, this is MB. PE, this is MB. And PE, this is MB. You should understand. See, and mostly during this kind of preparation, you must understand, you must be able to relate what are the concepts which are related to this current reading chapters, current reading content. So like that your mind should work. Alright? Okay, so let's move on. So here what I wanted to tell you, one important thing, work done. For example, let's forget about this magnetism concept. So let's talk about this one. Electric dipole. When electric dipole is placed in uniform electric field, what happened? That's the concept, right? So work done in rotating this dipole to some angles. Initially, it is at an angle theta 1 uncle, right? How much is the work done in rotating this electric dipole to an angle theta 2? So that's a top concept. So work done will have the formula, listen. So change in potential energy, which is final potential energy minus initial potential energy. So final potential energy formula is what? So initial potential energy associated with this you have, right? So minus PE cos theta 2. Initial potential energy is what? Minus PE cos theta 1. Alright. So change in potential energy you have UF minus UI. Change in potential energy. You get it? That's it. Now, for example, The question will be asked like this. So what is the work done by a force in rotating an electric dipole moment P bar when it is placed in E bar, like that. Work done by a force in rotating an electric dipole of dipole moment P bar when it is placed in E bar by an angle 90 degrees. Right? So, work done is equal to change in potential energy. Work done is equal to UF minus UI. Observe carefully. UF is minus PE cos 90 degrees, and minus of minus will be plus PE cos 0 degrees from the initial position. So, this is minus PE into cos 90 is 0. Plus PE into cos 0 is 1. What is the answer? What is the answer? So, P into E. So, that is the work done in rotating an electric dipole of dipole moment P bar when it is placed in E bar by an angle 90 degrees. And you will get the exam questions on this dipole moment also, right? Just get ready for this. That's it, right? So now let's talk about Gauss law. Gauss law and electric flux. Gauss law and electric flux. So what is Gauss law here? Imagine a closed surface. There is a charge Q is placed. The electric flux linked with this surface. See here. This charge will produce electric field lines in all the directions. This charge will produce electric field lines in all the directions. Like this, like this, like this. So electric flux associated with this closed surface is phi is equal to Q by epsilon naught. According to the Gauss theorem, if you write, listen, closed integral E bar dot ds bar is equal to Q by epsilon naught. So this Q is charge enclosed. That is important. This Q is charge enclosed. Right? So you all know about epsilon naught values also. Now, what is this E and ds? This ds bar is the surface area of this Gaussian surface. So what is this E bar? Electric field due to a charge. Electric field due to a charge. Now listen. Now listen. So there is a Gaussian surface, a closed surface is considered. So there is a charge Q1 is here. So there is a charge Q2 is here. Charge Q3 is here. And charge Q4 is outside the Gaussian surface. If you want to find electric flux linked with this closed surface, so closed integral E bar dot ds bar is equal to charge enclosed by epsilon naught. Charge enclosed in the Gaussian surface 1, 2, 3. Q1 plus Q2 plus Q3 divided by epsilon naught. While writing charge enclosed, we will not consider the outside the Gaussian surface charges. But we will consider this electric field also in writing this value. So I hope you understand. So E bar is the electric field due to the all charges, inside charges and outside charges. Whereas this Q is only the charge enclosed. That you should understand. That you should understand. Okay. Now, before we go to the applications of the Gauss law, listen carefully. Before we go to the applications of the Gauss law, and I am writing three important things here. So one is about lambda, another one is sigma, another one is the rho. So what is lambda here? Can anybody write what is lambda? What is the name? I just want the name. What is the physical quantity lambda? Don't write wavelength. Don't write wavelength. So lambda, what is lambda here? What is sigma here in this chapter? In this chapter. So what is rho here? Understand? So now the concept also I can tell you. So this is what the concept called continuous charge distribution. So whenever we talk about continuous charge distribution, we must understand these three physical quantities. So lambda is equal to a dq by dl, charge per unit length. Charge per unit length. So this is called a linear charge density. Linear charge density, charge per unit length. And sigma is charge per unit area. So this is called surface charge density. This is called surface charge density. And the last one, rho. Rho is called a dq by dv, charge per unit volume. What is that? Charge per unit volume. So this is volume charge density. This is volume charge density. So these three things will be useful for us while discussing about continuous charge distribution. While discussing about continuous charge distribution. Now, before we move to the applications of the Gauss law, let us discuss about, students, let us discuss about this one, electric flux. Let us discuss about the electric flux. So simple, electric flux, right? Look at this electric flux concept. For example, I have a cube. Carefully see. I have a cube. Inside a cube, there is a charge Q is placed. Now you know, this is the closed surface, which is a Gaussian surface. Inside there is a charge is kept at any place. Okay. Now electric flux linked with this surface is Q by epsilon naught for the system, right? So it is for the system. Now listen. There are some field lines will pass through each face of this cube, right? This cube will have 6 faces. So flux linked with each face of the cube is equal to Q by 6 epsilon naught. You all will agree with this? Yes. The total flux will be divided through 6 faces. Okay. Clear? So now the point is, so this is the first case, Uncle Ray. And the second case, we have kept a charge like this. This is the second case, kept a charge like this. In this case, what happens, you know? So we need to form a Gaussian surface. Gaussian surface, if you want to form here, there is an identical sphere must be kept. So there are 2 cubes now. So flux in the second case, flux linked with the system is Q by epsilon naught. Flux linked with each cube. Flux linked with each cube is Q by 2 epsilon naught. Right? Now the point is that, so third case, so we have kept the charge here like this. I hope you understand in detail. I hope you have studied this in detail during your electrostatics concepts. Okay, so now the charge is kept here, the third case. So to form a Gaussian surface, so there are total 8 cubes will come. So the flux linked with the system is equal to Q by epsilon naught. Right? So flux linked with each cube is equal to Q by 8 epsilon naught. Right? And in this case, flux linked with, so there are only few surfaces through which the flux will be linked. In this case, when the charge is kept here, there are through only some faces of the cube through which the flux is linked. Right? So when you take this cube, flux is linked with each face. I am talking about single cube. flux is linked with each phase. So that will be Q by 24 epsilon naught. Q by 24 epsilon naught. In recent exams, based on these three cases, questions were asked. In recent exams, based on these three cases, the questions were asked. That's the reason we are discussing this. Right? Now, let me rub this part. We are talking about electric flux and it's not yet done. Have a look at it. So there is another example. These all are the numericals. Another example. So there is a hemispherical body like this. Hemispherical body. We are not keeping a charge. For example, okay, we are keeping a charge here, Q. How the electric field lines will pass through this? The electric field lines will pass through in all the directions like this. Electric field lines will be passing in all the directions in this way. Okay. Actually, this is the surface is not closed. There is no Gaussian surface. Gaussian surface must be a closed surface. Okay. Now, we have to imagine a Gaussian surface here and close it. Then the flux linked with the Gaussian surface is Q by epsilon naught. It's fine. But what we need? We need only the flux linked with the hemispherical body. The flux linked with the hemispherical body is half of the total flux. Yes or no? So through the Gaussian surface also half of the flux will move. But it is imaginary. We have only this one. So the flux linked with the Gaussian surface is Q by 2 epsilon naught. Gaussian surface means so only half. But the given part, flux linked with this hemispherical body is Q by 2 epsilon naught when the charge is present here. For example, we have already discussed in the last class. So there is a cube here. There is a cube here. Charge is not kept inside. So the electric field lines are passing through this. So this is the homework what I have given. The flux linked with this cube is 0 we have got. 0. Why 0? Because electric flux is equal to charge enclosed divided by epsilon naught. So charge enclosed is 0 tane. There is no charge enclosed here. But here there is a charge enclosed in this imaginary Gaussian surface. And one more interesting thing. Have a look at it. So this is what hemispherical body only. Here the charge is not at all enclosed anywhere. So just it is kept in the uniform electric field line. See here. How the electric field lines are moving, you see here. How the electric field lines are moving, you see here. So such a beautiful and important concept of physics. So this is called the plane surface, right? So imagine you have a watermelon and cut it into the two halves. I am talking about the upper half. Upper half is here. So exactly the bottom part is a plane surface. Through the plane surface, the electric field lines will be passing. And from the curved surface also electric field lines are passing. So this is called a plane surface and this is the curved surface. Curved surface. Right? And it is clear that electric flux linked with the plane surface plus electric flux linked with the curved surface is 0. Net flux associated with this system is 0. Because how many field lines are entering through the plane surface? The same amount of field lines will be moving out of the curved surface. Net flux will be 0. Now listen. So electric flux linked with the curved surface is equal to minus electric flux linked with the plane surface. This question was asked in so many entrance exams. So this is the diagram they give and they'll ask you to find what is electric flux linked with the curved surface. Alright, electric flux linked with the curved surface is equal to minus, you know the electric flux formula here, EA cos theta. Carefully observe, electric flux linked with the curved surface is equal to minus E into area is pi r square into cos theta. I am talking about the plane surface. See, I am writing the expression for this. I am writing the expression for this plane surface I am talking about. So this is the plane surface. Field lines are moving like this. Area vector will be downwards. The last class we discussed about area vector. So electric field lines are moving like this. Area vector will be downwards. So in this case it is cos 180. Cos 180 is minus 1. Minus cancel. What is answer? What is the answer? Electric flux linked with the curved surface is pi r square E. Electric flux linked with the curved surface is pi r square E. Alright. So, previously in AIMS exams or in APMT exams, there was a question related to similar flux. There was a question related to similar concept of flux, and that question also we'll discuss. So, imagine there is a cylindrical structure like this. There is a cylindrical structure like this. Even in the cylindrical structure also, imagine this is the cylindrical object. There is a curved surface here and the plane surfaces from both the ends. This is the plane surface A and this is also the plane surface A. Curved surface B. Curved surface. The complete curved surface, I am just naming it as B. And the plane surfaces, I am naming it as A. Alright. So there is a charge Q is placed here. Charge Q is placed here. Now the point is, the flux linked with A and the flux linked with A plus the flux linked with the curved surface is equal to Q by epsilon naught. You all will agree? Tell me. The electric flux linked with the A, electric flux linked with the A, electric flux linked with the curved surface, all together that is Q by epsilon naught, net flux. So this is 2 phi A plus phi B is equal to Q by epsilon naught. You know the question is, flux linked with the B is given as phi. The electric flux linked with the curved surface is given as, curved surface is given as phi. So that's what I am writing here. 2 phi A plus phi is equal to Q by epsilon naught, and 2 phi A is equal to Q by epsilon naught minus phi. Super. So that is phi A is equal to 1 by 2 into Q by epsilon naught minus phi. So this is the standard question. This is the standard question in AIMS exams, APMT exams. This question was asked. If you want, you can check it in the previous exam questions. All the models what we have discussed is important. Right? So this is about electric flux. So let's talk now related to the applications of the Gauss theorem. Applications of the Gauss theorem. This is about the Gauss law related to the electric flux. Now the Gauss theorem. So I'm just rubbing it. If you want, pause the video and write it. 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 Okay. Now, the concept is applications of Gauss theorem. Applications of Gauss theorem. Very good. Applications of the Gauss theorem. Ready? So, what is the Gauss theorem? Closed integral E bar dot ds bar is equal to Q by epsilon naught, which is equal to phi. This is the Gauss theorem here. Number one, by using the Gauss theorem, you can find Coulomb's law, which is 1 by 4 pi epsilon naught into Q1 Q2 by R square. Let me share my experience with you in the last class. In the last class, some homework questions I have given, so where most of the students applied negative and the positive signs for this Q1 and Q2. You know in Coulomb's law, whenever you are talking about the Coulomb's force, understand? So those charges you should take only the magnitude, remember. You should take only the magnitude. you should take only the magnitude. Okay, clear? When you are writing an expression for electric field is also kq by r square, there q is only magnitude you should take. And here also the magnitude you should take, a magnitude you should take. Whether it is positive sign or negative sign, magnitude you should take. Remember. Alright, now the second thing is, so there is a line charge, my dear students. So there is a line charge. From this axis of the line charge at a distance r, electric field is how much? So this electric field is lambda by 2 pi epsilon naught into r. Very important. So E is equal to lambda by 2 pi epsilon naught into r. From here you can understand E is inversely proportional to r, and inversely proportional to r graph will be like this. Inversely proportional to r graph will be like this. So you can expect a question from the graphs, or you can expect a question like this. For example, lambda value. So lambda value is given as 2 coulomb per meter. Coulomb per meter, why? Because lambda is the linear charge density. So lambda is equal to dq by dl. So that's the reason coulomb per meter I have written directly. So epsilon naught value also you know, right? So epsilon naught value is 8.85 into 10 raised to minus 12 coulomb square per Newton meter square. I hope you remember this. And this R, for example, this R is given as a 4 centimeter. So that is 4 into 10 raised to minus 2 meter. So in this case, you can easily find the E value, find out this E value and send me in WhatsApp. Nobody is sending me in the group. Don't send me personally. Because when you send it, the other students will get motivated and they'll also keep sending. Right? So it's not about learning from your side, it is about interaction. So send the answer. Just substitute all these things here and send the answer to me. So in this way also questions can be asked, or in the graph also questions can be asked. So electric field, if you see, most of the students will just think electric field is inversely proportional to r square. Yes, of course, electric field is inversely proportional to r square. That is due to the point charge. And that's what the third case. Third case, there is a point charge q here at a distance r. Electric field is kq by r square. For a line charge, electric field is lambda by 2 pi epsilon naught into r. Right? Now, the fourth case you see. Students, the fourth case. If you have a sheet, plain sheet. If you have a plain sheet which is non-conducting, clear, look at here. Plain sheet which is non-conducting and the plain sheet which is conducting. Infinite plain sheet, conducting and non-conducting. If it is non-conducting, electric field is sigma by 2 epsilon naught. If it is conducting, electric field is sigma by epsilon naught. Clear? So for example, see from this plate at a distance r, this is the electric field. This is the electric field. So if it is non-conducting, that's a value. If it is conducting, this is the value. Imagine what is sigma. Tell me what is sigma. Students, what is sigma here? So sigma is the surface charge density. Surface charge density. And one more important thing. So which case, in case of conducting, sigma by epsilon naught. Sigma by epsilon naught you will get exactly when both the sides surface charge densities distribution is same. Okay. Alright. Clear? Good. Now the number 5. See how many things we are discussing. And one more thing. So let's talk about this one. So this one, if you draw the graph between E and R, so this is the graph. See, beautiful graph. No confusions. So it is constant. Whatever may be the R value from this plate, this is the plate. So at any position, if you keep the point of consideration, electric field will be constant. That is depending on surface charge densities. Look at here. That's depending on surface charge densities. Depending on surface charge densities. So this case, electric field, in case of a plain sheet, conducting or non-conducting, electric field is only depending on the sigma. That's it. Independent of the distance. So that's a very important graph. And number 5, see how many cases we are discussing. So it is not like revision actually, it is right, it is like the actual class what we are doing. Okay, so here two things I wanted to mention. So number 1, it is what I can say, it's a conducting sphere or a shell. Alright, conducting sphere or a shell. So conducting sphere or shell where the charges will be distributed on the surface of it. So in this case, inside electric field is 0. Inside at any point you take from the center. So the radius of this is R. On the surface, it is KQ by R. On the surface, KQ by R square, sorry. On the surface. Alright, I am talking about this is E on surface. And KQ by small r square from here, for example, at this distance, which is E outside the shell or conducting sphere. So how the graph will be written here? The graph can be drawn like this. Listen, E and R. This is the center. From the center to the surface, E value is 0, right? So E value is 0. Till where? Till small r is equal to capital R. So E value is 0. From here, it is inversely proportional to R square. Very important. See the graph. We are talking about the shell, right? And little advanced concept in the shell. I just wanted to do a quick recap. And there is a shell here which is given a positive charge Q1. And there is another shell is considered here. So which is given a positive charge Q2. Fine. A charge Q2 is mentioned for this. A charge Q2 is mentioned. So here a charge, it's radius of this inside concentric shell is A and the radius of this concentric shell is B, right? And you all know that, listen, you all know that there is a common center for this. Inside the shell, electric field is 0. Outside the shell, electric field is not 0. Because this is the point outside this shell, inside of the second shell. Right? And at this point, electric field is there due to this shell as well as this shell. Whatever may be, the formula for the electric field is KQ by R square. Alright? I hope you got the point. So, this is the point electric field. Most of the students will think it is 0. No, because it is inside the shell, it is 0. But it's wrong. Because it is inside of the second shell, but outside of the first shell. First shell is having a charge Q1. For example, this is the point is at a distance R. Electric field due to the first shell, it is KQ1 divided by R square. So at the same point P, electric field due to the second shell, it's a 0. Okay? Clear? So like that. So the net electric field is E1. Now, the last concept of the first chapter of electrostatics is, so there is a sphere, there's a sphere, and this is a sphere which is a non-conducting sphere, and the charges will be distributed throughout the volume of the sphere. The charges will be distributed throughout the volume of the sphere, like this. So this is the center. The radius of this non-conducting sphere is R, you know. So inside E is inversely proportional, directly proportional to small r. For example, here this is my point of consideration, which is at a distance small r. That small r is lesser than capital R. Electric field will be increases, reaches to the maximum value on the surface. So on the surface, the electric field is maximum, which is K, so Q by R square. So imagine the charge present on it is Q, right? And rho is equal to this Q by V, total volume, throughout the volume, charge per unit volume. Throughout the volume it is shared, it is distributed. Okay, so now this is on the surface. So now outside the surface also you can write, outside the surface it is E is equal to KQ by small r square. Yeah? So for example, the point is considered here. The point is considered here. Outside it is KQ by r square, right? So if I draw the graph for this, so look at here, students. So for the same, if I draw the graph, so this is E and this is R, right? For the same, if I draw the graph, graph is like this. This is center, right? This is center and the graph will be like this. From the center to the surface, R is equal to capital R. Electric field is directly proportional to small r. See, there is an expression for this. I am not writing it here. You just go through the expression also. So, because our focus is about the graphs here, you may get a graph. And so when you understand these graphs, the graphs for the electrostatic potential concept will be easy. And the graphs for the acceleration due to gravity will be easy in electrogravitation. The graphs for gravitational field intensity is also easy. So outside the surface, you can see from the surface to the outside. So electric field is inversely proportional to R square, right? Remember this. You know, acceleration due to gravity graph also you will get the same. You can consider this as, this is a non-conducting sphere. You can consider this as a surface of the earth. This is the earth you can consider. Earth you cannot consider as a shell or a hollow sphere. So this is the sphere, solid sphere. So you get the acceleration due to gravity is also acceleration due to gravity and small r graph exactly same. Small g is inversely proportional to r, small g is directly proportional to r, small g is inversely proportional to r square. Exactly the similar graph you get it. Okay? Clear? So that we'll be discussing in the gravitation chapter. So I hope you understand the discussion so far, and let's conclude this section with a single problem, with a simple problem. Alright? Let's move on to this numerical. Electrostatic potential inside a charged spherical ball is given phi is equal to A r square plus B. Remember, it's not electric flux. To confuse you, they have given like this. Electrostatic potential is given. V is equal to phi, which is given as A r square plus B. Where r is the distance from the center, A comma B are the constants. Fine. Now, charge density inside the ball they are asking. Charge density inside the ball. So what is the charge density inside the ball? This is the spherical ball they have given. Charge density in case of a spherical ball, it is rho, which is equal to Q by V, charge per unit volume. So this is V you have. Whenever this V is there, and you can have the relation dV by dr. Okay. R is the distance, V is the potential, E is the electric field. Right? Now, because they are talking about the charges and they are talking about the potential. Charge will create an electric field and the potential. So this is minus d by dr of v. V is ar square plus b. So this is minus d by dr of ar square. So that is 2ar d by dr of b, that's a 0. So you have electric field. According to the Gauss law, closed integral E bar dot ds bar is equal to q by epsilon naught. E comes out, integral ds. So this is the sphere, the surface area of the sphere. It's a 4 pi r square. This is done, left hand side. This q naught, epsilon naught will come here. So that's a q. What is this E? E we have just found from here. 2a into r, 4 pi r square into epsilon naught. That's q. Our aim is to find rho value, which is q by v. So the rho value is equal to q by v. Q is minus 2ar 4 pi r square epsilon naught divided by v, 4 by 3 pi r cube, volume. Pi r cube cancel. See. So what is left here? What is left? So this is 4 also cancel. Here it is minus, this 3 goes to the numerator, that will be 6 a epsilon naught. Yes, nothing is left. Yes, minus 6a epsilon naught. So this is the value of your rho, which is the charge density inside the ball, which is exactly called volume charge density. Okay, so this is the answer. Very important question. Now, so when we talk about the little higher thing, little higher than this, we have understood and we have discussed so many graphs. Now, electric field. Sometimes the question paper to be hard, they may give you this also. Electric field due to a ring, which is a charged ring. Electric field due to a charged ring. So look at this. This is the ring we have, which is a charged ring of charge Q, and the radius of it is R. Look at here. At a distance x, we are going to find the electric field. You know the formula for this. E is equal to kqx by square root x square plus r square whole to the power 3 by 2. You must remember this formula. Kqx by kqx divided by x square plus r square whole to the power 3 by 2. So what is x? X is the distance between the point of consideration and the center. R is the radius. Now, in this case, if I want to extend a little bit, E value will be 0 at the center. And this E value will be maximum, the maximum value, which is equal to, it is maximum value is possible at x is equal to plus or minus r by root 2. Towards the left side at a distance r by root 2. Towards the right side at a distance r by root 2, you get the maximum value of E. What is that maximum value? This x value, substitute r by root 2, you substitute here, you will get it. So sorry, in the place of x, you substitute r by root 2. Here also r by root 2. What is that? E maximum value, you will get it. Alright. You remember this one. No need to remember this formula. So remember this formula. At this x position, if you put r by root 2, and it is easy. You can do that. This is how electrostatics 1 is finished. So that is called electric charges and fields concept is done. In the next class, we are going to finish electrostatic potential and capacitance. We are going to finish in next one class, and get ready for that. All the very best and prepare well for your evening exam. Thank you so much.